We should be good. Awesome. So today we're talking about Docker containers and orchestration. This is week 10 of the Code Foundry Free Tech Bootcamp. And so list of the items that we're going to be going over today. We're going to be talking about going over application architecture one more time. We might go through this another two more times in the last two meetings, but that's just because it's so fundamental to understand how these different applications types are formatted and architected. And then following that, we're going to go into containerization, which follows through with our thread on microservices. So we've been talking about microservices from week 5, but this time we actually talk about what is a microservice and containerized application at that. Following that, we're going to talk about containerization with Docker. We're going to follow that up with introduction to container orchestration, and then we're going to go into Kubernetes orchestration. Finally, the last thing you'll note is that we are ending our talk with a question, which is how much am I worth? And that's going to basically be a discussion about how much a developer or an engineer is worth in industry. How much should you be charging if you're an independent contractor? How much should you be getting paid? And I just ran through my statistics on that today, so I hope that could bring some light to that topic. And then finally, we'll go ahead and go through our projects and have project check-ins. And our take-home videos for this week are containerization with Docker and orchestration with Kubernetes, which will be coming out on Tuesday and Thursday, respectively. So a little bit about Code Foundry. I can see that we have a couple new faces today. Welcome in. It's super awesome that y'all got to join us. Code Foundry is a 12-week program that is being put on by Hispanic Hackers. And if you're new here, don't worry, we accept everybody who comes in. Hispanic Hackers is a nonprofit organization based out of Austin with the goal of making the tech industry more accessible to Latino and Hispanic people. We're a very inclusive organization, so we welcome all the different kinds of backgrounds, but our goal is really to help advance our tech careers through a network of engineering excellence and a set of resources that all can glean from and grow from. And so we put on programs just like Code Foundry to basically help our community level up. And this event is also sponsored by Circle Square Labs and Capital Factory. Circle Square Labs is a development firm out of Austin with the goal of basically meeting client needs when it comes to front-end, back-end, DevOps, cloud, and other development schemes. And then we have Capital Factory, which is our in-person host. They are a co-working space here in Austin and a great spot to meet new people, especially through the plethora of networking events that run through them. And so the goal of Code Foundry is really to get developers and entrepreneurs in the same room, working on the same topic and understanding the background behind technology, right? I work as a contractor, and I've realized that there's a lot of startups where the owners don't understand the technology that they're working with. And so my goal is to be able to educate not just the startup owners, but also developers who are trying to get a stronger grasp on the tech industry and be able to lead everybody through the different topics that industry covers and requires us to know as software engineers. So moving in to a recap on application architecture, we'll go through this fast because we've talked about this almost every meeting since week 6. So there are a couple different architecture types. This is the monolith, and this is the basic architecture type that you think of when you just think of an application that you download and run. And the idea behind the monolith is that you have an application, and that application sits on a user's machine. It has maybe dependencies and assets tied to it, but it's all internal. And you might have some external resources. Maybe you contact an API, or maybe you retrieve some images from online. But the idea behind the monolith is that it's largely independent, and it only is updated when a user goes ahead and installs a new updated version of the application. So some drawbacks to the monolith is that It doesn't automatically update. It's not connected to many resources or anything like that. It's pretty standalone. This could be like Flappy Bird or your basic application. And some benefits, however, are that it's really simple, because you don't have to set up external resources. You don't have to pay for servers. You don't have to do anything there. So it's a pro and con. But next we're moving into front end and back end configuration, which is really what a lot of people think of when they think of a application which is server side, right? When you have a front end and a back end. And the idea here is that you have your front end with your front end dependencies and assets on the user's machine, but that front end contacts a server, which will contact and retrieve external dependencies, or it'll contact external resources. So maybe it contacts a database with user information and retrieves that user information and returns it to the front end. And the idea of separating back end and front end logic is that the back end logic is hidden from the front end. So the benefit there is that you have a little bit more discretion in your front end and back end logic. And another couple of benefits is that things like user authentication and other topics in that realm can be maintained with secrecy and privacy. So you have a greater control of privacy. You have a lot of server-side components and services that you can bring in as well. There are a lot of benefits as well as drawbacks. And some drawbacks would be that you have to pay for server time. You have to set up orchestration in terms of how is my application going to run on a server that I'm not controlling, or how am I going to set up a server that I do control to run the application. So when you think of a back-end front-end configuration, which is pretty typical, you also have to think of how is this going to be hosted and how am I going to update it, run it, etc. And we've talked about DevOps, we've talked about a lot of different topics and cloud, and we've talked about how these programs get run in past meetings. But that's the second most basic type of application architecture. Following that, we have a containerized service architecture, and this is what we're going to be talking about today. The idea behind a containerized architecture is that we are wrapping our backend application or our application in a container. And what this container does is it holds all of our dependencies and assets, and it can be spun up on any server or any machine that has a container runtime. And we'll talk more about what this means in a little bit, but the idea is that a container is a compartmentalized format of our application which contains external dependencies in it and can also be configured to have external access to external resources. And it can be run on a server or virtual machine with ease. And another benefit of this is that you can have multiple of these containers running at once. As you can see, we have multiple of these containers on this server. So part of why containerization is so important is that it provides application isolation, which is required when you upload your application to the cloud, because when you upload your application to a cloud server, most of the time your application is going to be hosted alongside dozens or hundreds of other applications. So you want to make sure that your application is isolated from those applications but has the dependencies it needs to run. Next, we have a abstracted version, and you might be able to notice that every single one of these diagrams is abstracted from the last. And that's the idea, is that we're expanding our knowledge of application development over time, and we've been doing that in our program. The next iteration is microserviced. And what microserviced is when you have multiple containers working together as small compartmentalized services. And the benefit of this is that, say you want to update one of these external resources or one of these other containers without affecting the backend container or this container here, you can just update that container with ease and it won't affect any of the other parts of the application. Similarly, we could switch out the backend container with a new updated version, and it wouldn't affect the external resource or the front end. And the beauty of microservice system is that you have multiple services, multiple small compartmentalized applications that work together and can communicate with each other. And the benefit there is that you can maybe say you want to save one of these external resources and use it in another application. All you have to do is bring that container into the other application. Or say you want to update one part, you can update it with ease. And so there are a lot more benefits to microservice applications. However, the downfalls is that it could be overly complicated if all you have is a basic application or basic program. And so my recommendation whenever we have a more basic program where we need to have a backend, but we don't want to set up a whole backend running on maybe an EC2 instance or some application instance on the cloud, is to use a serverless backend. And so what a serverless backend is it's a cloud-hosted backend where you break down your necessary backend components into small functions, which get containerized by the cloud provider. So the cloud provider will just allow you to upload your code gets containerized, and it gets stored onto the cloud. And the nice thing here is that our backend functions will be able to talk with our assets and external resources that are all hosted by the cloud provider with ease. And so there's greater connection here. And the nice thing here is that you only get charged for when you actually run the application. Versus with these other formats, you get charged the whole time that the application is running, which for a backend front-end model, that is all the time. So that is one thing to note, is that serverless model is very efficient because you only get charged for the time that you actually run the application. And so that's essentially where we're headed. Is we talked about serverless models last meeting. This meeting, we will talk more about microservice and containerized applications. So now we're going to talk about what is containerization, what is a container, and what does that mean? The first thing that I wanted to preface with is I wanted to preface with what is a virtual machine, which a virtual machine is important because it's the first step that leads us into containerization. A virtual machine is a software-based emulation of a physical computer that runs on an operating system. What that means is that it's kind of like having an isolated environment. And a lot of y'all have probably worked with virtual machines before. They're very popular, and it's so that you can maybe run like Linux on your Mac OS or on your Windows computer, or so that you can run, Windows on your Mac OS. And so VMs or virtual machines use a software layer that allows multiple operating systems to run concurrently. That's called a hypervisor. Each virtual machine includes a full OS or operating system, binaries, libraries, and application code. And some key features is that you have full isolation of the operating system and resource intensive. It is resource intensive because it has to have its own operating system. And it's ideal for legacy applications or heavy workloads. This is what we used before we had containerization, is we used virtual machines to isolate our code and on servers. And that was nice, but it wasn't very effective. So following that thread, after the birth of virtual machines, we came up with a concept called containerization. And what containerization is it's the process of encapsulating an application and its dependencies into a lightweight portable package. And the idea behind containerization is that you no longer have to have an operating system on a virtual machine, but instead all you have to have is the packaged code. And the packaged code or container can be run on any operating system as long as it has a container runtime installed. So the nice thing about this is that now you have lightweight portable packages, and it's kind of like having a container on a ship, right? And the idea there, when we think of containers, we're always thinking of of docking ships, or like shipping containers, where we package all of our code into that shipping container, and then as long as there's a ship around, we can actually run those containers, right? The ship being the container runtime. And so we can now consistently run our application across various environments. Some key characteristics are that containers are lightweight, they're portable, and they isolate your application or run your application independently of others. Why it's revolutionary? It solves the "it works on my machine" problem, where say you're in a company with 20 developers all working on the same project. Instead of having to set up all of their operating systems specially to run the application, or setting up the application so it could run on every single operating system, now all you have to do is package it as a container and send it to the other person who has the container runtime installed on their machine. The container runtimes each have operating system versions, so all you have to do is install it for your operating system and then run the container. So that's amazing, because now we don't just need it, and we don't need to install new virtual machines so we can run these applications. Now it just works on your machine no matter what. And then it also facilitates microservices architecture, which we've touched on why that's so important and what the benefits are there. So how does containerization work? The first thing is we want to package the application. So the application, libraries, and dependencies of your application are all bundled into what we call a container image. An image is just a tar version of your application. So what is it? Something application resource? I forget what tar stands for. But it's just an archive. It's an archive file. And essentially, what it does is we bundle our application into an image, which is just a file with all of your application data in it, as well as some Docker configurations or some containerization configurations. And so an example of that would be our Node.js web app packaged with Express and required libraries. Then we can send this container, we can store it in a repository if we want to, we could send it to other developers, and what they can all do is they can all run the container using a container runtime. So the most popular container runtime is Docker, and we're going to talk about that today. What the container will do is it'll share the host operating system kernel and minimize overhead. And so running the container, it'll run efficiently on our container runtime, and it can run on any operating system as long as you have the container runtime installed. Some results are consistency and efficiency. The same image can run on a developer's laptop, a test server, or production. And containers will use less memory and boot faster than virtual machines. So now that we've talked about containerization, well, let's move into Docker containerization, which is using the Docker container runtime and the Docker packaging system. So first up, does anybody have any questions? Kind of rushing through here, and I want to take a step back. Everybody good? More or less, yes. So like before we had containers, we would have to essentially either create an application so that it has multiple formats that meet the standards of iOS, Windows, or Mac OS, or whatever operating system it's going to run on. Or we would have to install a virtual machine on everybody's laptop, which runs the same operating system. However, now that we have containers, all we have to do is package it using the container application or Docker, for example, and package it. And the idea behind it is that it creates a operating system agnostic format. It creates a format that could be run on any operating system as long as that operating system has the container runtime to run it with. So what it does is it kind of abstracts and formats your application so that it could be run on a special program such as Docker. Does that make sense? Sweet. Any other questions? Awesome. So what is Docker? Docker is an open source platform designed to build, ship, or deploy and run applications inside lightweight portable containers. How it works is that applications and their dependencies are packaged into a Docker image. So all you do is you combine all of your application and its dependencies into a Docker image. That Docker image could be sent to a developer, it could be run on your computer, it could be run in production, and these images are executed and isolated containers using the Docker image engine. And then finally, containers share the host operating system kernel, making them faster and more efficient than virtual machines. So you don't have to install other operating systems, you just use your own. The key use case is that you have streamlined development and testing, simplified deployment across environments, and enabling microservice architecture, which again, we've covered. So some core components of Docker are you have the Docker engine, which is the runtime responsible for building, running, and managing containers. We have Docker images, which are read-only templates containing the application's code, libraries, and dependencies. So once you compile into a Docker image, you can't edit it anymore. You have to recompile from your application's code to do that. Docker images can be run on runtimes other than Docker image. So that is engine. So that is one thing to note. There's, for example, container RD is or containered is another container runtime that's not Docker engine. Docker containers are instances of Docker images. So what you do is you take a Docker image and you spin it up or run it to create a container from that. And then there's also Docker Hub. Docker Hub is a repository for storing and sharing your Docker images. So you can find public Docker images for things that you might need in your application. For example, in a microservice architecture application, you might find a Docker image that you can pull in that could say run an AI or run some kind of process, maybe do authentication for you. And so the idea is that Docker Hub is a public and private repository for storing and sharing these Docker images. Finally, you have the Docker CLI or command line interface, which is how you interact with the Docker engine to build, run, etc. So why use Docker? Docker integrates with orchestration tools, which we're going to talk about orchestration. For managing large-scale deployments, it has a huge ecosystem, and that's the really great thing about Docker. So this is a diagram of essentially how containerization works. On the top right here, we have our source code, maybe our framework files. So for example, our React app. We have our libraries, which are, maybe JavaScript. So here we have our JavaScript application. And then we have an additional file called a Docker file. And this Docker file is a special kind of file which essentially sets up the application when we run the image. So when we run our image and turn it into a container, what the Docker file does is it goes through step by step how to spin up your application. So it's the instructions that you give your application. For example, we say maybe npm run to run our Express app, right? Or npm start. That command is going to be given in our Docker file. And so we write that command into our Docker file to tell our Docker file or our Docker container to run npm start to start up our application when the Docker container is spun up. So the Docker file is basically just a list of commands to tell our container what to do when it starts. And then maybe you'll add in other commands in there too, maybe set up environment variables or run other processes. And so what we do is we take our container image and we containerize we take our files and we containerize to create a Docker image, which is just a tar file. And we can store our tar file on a container registry. For example, we could store it on Docker Hub, which is a repository for us to store our containers in. And it's a cloud-based repository. Finally, we can take our container images from the registry and we can pull it onto our operating system. And what it'll do is it'll store our image and run it using the container runtime. And running or spinning up an image basically converts it from an image into a container. So an image is like a flat file, a container is our actual application. And when we run it, what will happen is our container will look for our Docker file, find the commands in our Docker file, and set it up according to the commands in our Docker file. So what our Docker file is it's just a list of commands on how to set up our application when we run it. And as you can see here, we can have multiple containers within our container runtime. They can be running at the same time. They could just be there stored. And that's the nice thing about Docker is that it gives us a wide variety of options for manipulating and storing our Docker containers and images. Some benefits of containerization are portability. Containers run consistently across different environments. Efficiency. Because they share the same operating system, you reduce overhead and improve performance. Rapid deployment. You can start containers very quickly compared to virtual machines, which take a long time to boot up. Scalability. You can easily scale applications horizontally by spinning up more containers. And then isolation, which is keeping applications and their dependencies separate to avoid conflicts. Some challenges with containers are resource management and scaling. So for example, how do you manage the resources on your operating system to be able to run effectively all your containers, and then also provide network resources. And so our solution to this are providing resource limits and container orchestrators for setting up multiple containers at one time and running them together. Networking complexity. Networking complexity gets complicated when we're communicating between multiple containers, hosts, and external systems. And so our solution to this are setting up orchestrator network policies and service discovery. And again, we'll get into orchestrators in a minute, but the idea behind an orchestrator is that it allows us to communicate and run multiple containers at once in a microserviced format. Data persistence, monitoring, and debugging. So everything that happens in a container stays in the container. Containers are ephemeral by design. And what ephemeral means is that it means that when a container shuts down, nothing is saved. The containers lose all of the data that they created. And so in order to solve the problem of data that we want to persist after we've shut down our container, we use persistent volumes, cloud-based storage, and then logging and tracing applications to help us continue data outside of our container when we shut down our container. And this can also be set up with orchestrators or other applications or programs that we can install on our containers. And then finally, security concerns. Shared operating system kernels between containers can introduce vulnerabilities. So what we do is we set up namespaces, C groups, and image scanning. And image scanning is a way for us to scan our images for vulnerabilities in our application. And that's another really great thing if you're wanting to create a cyber secure application. So we've talked about some issues and some deficits of our containers. How do we run them together so that they communicate appropriately? How do we set them up? Because right now, all of our containers just run in isolation. And Docker Compose is one of the methods that we can solve this problem of how do we run our containers together. Docker Compose is a tool for defining and running multi-container Docker applications on a single host using a YAML configuration file called dockercompose.yaml. Now, the nice thing is that it simplifies managing dependencies for multiple containers. It supports defining volumes, networks, and environment variables, and automates container startup and shutdown with a single command. However, the deficit of Docker Compose is that it's only for a single host. So say you're running your applications on the cloud. Sometimes on cloud architecture, your application or different parts of your application, different containers, will be run on different servers. So in that case, you don't have a single host, you have multiple hosts, and you might have one container running on one host and another on another host, and you want them to still communicate. And so our limitations is that we're limited to single host deployments, and we lack advanced features like auto-scaling, self-healing, and load balancing. Some use cases would be for local development and testing, or managing application environments without needing a full orchestration platform. So Docker Compose solves half of our problem, but it doesn't solve everything. And so to solve everything, we are going to use container orchestration. But before we get into container orchestration, we're going to take a 5-minute break to get water, go to the bathroom, whatever you need. So we will meet up back at 7:47. I'll see y'all in a minute. we're gonna get back to it. Before we do, does anybody have... All right, we're gonna get back to it, but before we do, does anybody have any questions? Okay, it sounds like nobody has any questions. If you all have a question, feel free to unmute pretty much any time and interrupt me. We're going to move on and talk about orchestration and orchestrators. And what orchestrators are is that they're a method for running containers in groups to be able to perform multiple functions in a microservice kind of configuration. And so, without further ado, let's get started. A container orchestrator, or the container orchestration, is the process of automating the deployment, scaling, networking, and management of containerized applications, especially multiple containerized applications. Some key tasks are scheduling, so placing containers on appropriate hosts and determining when they get spun up, etc. Scaling, which is auto-adjusting the number of containers to match workload demands. So say you have more users come onto your app than you actually planned for, and you need more containers. You can set up auto-scaling or auto-adjusting the number of containers needed to match the new demand for that application. Networking, which is managing the container communication or the communication between containers. Monitoring, which is ensuring applications are healthy and operational. And then fault tolerance, which is restarting or redistributing failed containers so that you don't have to go in manually to restart it if something happens. Some examples of orchestration tools include Kubernetes, Docker Swarm, Apache Mesos, and Amazon ECS, or Elastic Container Service. Docker Swarm is the Docker equivalent of Kubernetes to some extent, but it doesn't exactly meet all the same. It's not as industry standard, I guess. So that's why we're talking about Kubernetes rather than Docker Swarm. Why apply orchestration? Orchestration allows for efficient resource utilization. So maximizing use of CPU, memory, and storage access across multiple hosts in a cluster. So being able to make sure that we don't exceed one host's memory capability. Simplifying management, so reducing manual effort by automating deployment, scaling, and recovery tasks. Scalability, handling dynamic workloads by easily scaling services up or down. Reliability and fault tolerance, so automatically detecting when a container has failed and restarting so that we maintain application uptime. Simplifying networking, so providing networking assistance so we can communicate between our containers. And then multi-host deployments, where we have multiple hosts, we have a bunch of containers scattered across those hosts, much like in cloud service configurations. And so some core components of orchestration are a cluster, which are a group of interconnected machines or nodes working together to run containerized applications. And within these machines or these servers that run our applications, we have a master node, which manages the cluster, schedules workloads, and monitors. And that master is composed of a bunch of different components, two of which are the scheduler, which decides where and when to deploy containers, and the controller, which ensures the system's desired state is maintained, such as the number of running replicas on healthy containers. Worker nodes are the servers or hosts that execute the workloads or execute the containers as instructed by the master node. So the master node will tell the worker nodes when to spin up and how many to spin up of your container. And so again, this is the case where you have your application spanning multiple servers and you have multiple containers to communicate between each other. You could also just set it up so that you, for applications where you only have one server running everything, but you have multiple containers and you want them to communicate with each other. Pods are the smallest deployable unit containing one or more containers. So pods are our groups of containers that we are orchestrating. A load balancer is a method for distributing traffic across multiple container instances. It's a component that ensures availability and reliability. Service discovery enables containers to find and communicate with each other. So it's our networking system. And then we have networking, which connects containers, nodes, and external systems using overlaid networks or service meshes, and service discovery operates on a network. And then we have storage management, which allows us to handle data persistence, so allows us to manage our data that's created inside of these containers and store them somewhere, usually on the master node, after we shut down our containers or while our containers are running. So how orchestration works is we prepare the cluster, we set up a cluster of nodes, and you always have to have a master and then multiple worker nodes. You install your container runtime and orchestration tools for your cluster, and then you configure networking between nodes. And this can all be configured and determined by config files that are given in your application. We define application configurations, so we write YAML or JSON configuration files to describe our pods, services, and deployments, and then we deploy to the cluster. And we use the orchestration tools to deploy. So for example, in Kubernetes, we use kubectl, which is their CLI tool, to apply configuration files and launch the application. The orchestrator will schedule the deployment by determining where containers should run. And so that's the idea behind Kubernetes. It's basically a system for setting up your containers in a way that they can run either all on one host or on multiple hosts and sync together. And so Kubernetes is just that. It's an orchestrator. And we've been talking about orchestrators this whole time. But Kubernetes will be an orchestrator that is very popular in industry, and that's why we're talking about it today. It's an open source container orchestration platform designed to automate deployment, scaling, and management of containerized applications. It was developed by Google, and now it's maintained by the Cloud Native Computing Foundation. And the purpose is to be able to handle complex systems of multiple containers across multiple machines called clusters of machines. Why use Kubernetes? Kubernetes is manages hundreds or thousands of containers efficiently, meaning that it is perfectly fine for a small system all the way to a super giant system. Kubernetes also ensures high availability and fault tolerance with a lot of features for making sure that your application is always available, and it simplifies scaling, updates, and resource management. So persistent storage, how your application scales, and how your system updates. Kubernetes architecture is as follows. You have your master node with an API server. And so the API server is the central interface for managing the cluster. You have your scheduler and your controller, and these just make sure that your workload is appropriately scheduled, so you're spinning up your containers on the right servers, and it manages the state of the clusters and ensures desired condition. Then you have etcd, which is the key value store for cluster data and configurations. In addition to the master node, we have our worker nodes, which have kubelet, which is managing our container runtime and enforcing pod specifications. They also contain a kube proxy, which handles networking and routing of traffic between the containers and also outside of the containers. And then we have the container runtime, such as Docker or container RD or container D. Container D? I think it's container D. Containered, which run the actual container. You have your networking or your network, which provides communication and service discovery between the nodes and the containers. Some key Kubernetes components are pods, which are the smallest deployable unit in Kubernetes, which one or more containers. You have your nodes, which are machines in a cluster. You have your service, which is, oh, and one thing to mention here is that our nodes can be either physical or virtual machine servers themselves, right? So you could have multiple virtual machines on a host, on a single server. And then on there, you could install Kubernetes to manage containers on different virtual machines. You have your service, which exposes an application running in a set of pods to the network. You have, which has to do with service discovery, of course. You have your deployment, which manages the state of the applications, which includes scaling and updating. You have your namespace for isolation, config maps, and secrets for managing the configuration and your environment variables or sensitive data. And then you also have persistent volume, which is for storing data even when those containers shut down. And then you also have an ingress controller, and this is essentially a specialized controller for managing and routing external traffic to services within a Kubernetes cluster. Some benefits of Kubernetes is automated scaling, so adjusting the number of pods based off of workload demands, fault tolerance, efficient resource utilization, portability, so making sure that everything is portable and you can consistently run on different operating systems or multiple machines, rolling updates and rollbacks, so ensuring that there is zero downtime. So basically when we update, we'll spawn new containers with the updates on them and then roll into them without having to shut down the other containers first, have downtime while we update them, right? And then service discovery, communication between our microservices essentially, and extensibility, which is supporting custom workflows with plugins and integrations. So as mentioned, Docker has its own orchestration tool called Docker Swarm. The difference is that Kubernetes is a bit more complex, but it also provides fine-grained and automated scaling, high configurable networking, advanced resource monitoring tools, a very large ecosystem, lots of strong availability with multiple master nodes, and then a large-scale complex application use case, where essentially we're trying to run a complex application on multiple machines. On the other hand, we have Docker Swarm, which is a lot more simple, easier to set up, faster in scaling, but it's less advanced. It is built into Docker Engine naturally, so it's simple for networking. Resource management is pretty simple and basic, and it has a more limited ecosystem. Availability is not as strong, and it has limited fault tolerance, and then it's more simple, small scale. Or that's the use case. And so essentially, as mentioned here, the use case for Docker Swarm would be if you have a simple application that you're deploying on a limited number of machines, versus Kubernetes is a lot more complex, but a lot stronger when it comes to deploying on a large network of machines. And so here we have our diagram of how our containerization was set up in the first place. And we had our Docker file along with our other source code and frameworks and libraries. That gets containerized into a tar file. And then when we run a tar file image, which is our container image here, we spin it up into a container which can run on our container runtime. When we implement Kubernetes or another orchestrator, we add our orchestration files to our Docker container image, as well as other parts of our source code. And what this does is this allows us to spin up our containers individually. And then when it gets packaged, our containers will communicate with the orchestrator, which has its own configuration files to run any number of containers. So that orchestrator will communicate back and forth with the container runtime and the containers in it to make sure that our containers get spun up appropriately. So what we've talked about so far has been very abstract. This is how it's all implemented. Here you can see we have a folder or a directory called microservices. And in it we have multiple services. We have two services here. We have service 1 and service 2. Service 1 is a Python application. And in it we have our Kubernetes deployment configs, we have our Docker file, and then we have our source code. Our Kubernetes components are a deployment, service, and ingress controller YAML files. What YAML files are is they're just like JSON files where they are configuration files that are easy to write and simple. Similarly, we have a second service, and in this service we have a JavaScript or a Node.js application. We have our Docker file, and then we have our Kubernetes files, which are the exact same as the other microservice, but maybe we set them up a little bit different. Maybe we provide some different environment variables. Maybe we provide some different routing information, or maybe we give some scaling information that isn't in the first service. And then finally, we have our Kubernetes directory, which is within our microservices file. And what this Kubernetes directory does is this Kubernetes directory has information for our namespaces, so how we isolated these containers, an ingress controller for communicating between the ingress YAML file or the ingress system inside of these containers, and a persistent volume configuration file. And so we'll go through each of these separately, but the last thing to note is that we have a Docker Compose file here, and that Docker Compose file is for running Docker Compose for a local development or orchestration environment. So when we're developing the application, we want to test this out, and we'll test it out using Docker Compose instead of Kubernetes, because Kubernetes is more for when you deploy the application onto multiple host systems rather than on just one testing or development host system, right? So we have that Docker Compose there for local development purposes. So now let's dive into these Kubernetes files. The first one is deployment. And what this does is this configures the number of replicas we need, our image, and our environment variables. So it's the basic file for setting up our orchestration or orchestrating our containers. Next, we have a service file, configuration file, which basically sets up our network and access endpoint for our application. So how is our application going to be accessed by other applications? The way it works is that we set up an API between applications, which all it is that it's a service in between, a network in between, where we can make requests and return responses back and forth. And then finally, we have our ingress routing or config, which allows us to set up our access and routing configurations for our service specifically. Down here, you might notice a requirements.txt file. This is for our Python file here. And basically what this requirements.txt file is going to have is it's going to have a list of libraries that this application needs. Similarly to the package.json file down here, which has a list of libraries that our app needs. And so as you can see, we have the exact same content in our Kubernetes files. It's just maybe set up in a different way for our second service. Down here we've already gone through our namespace, ingress controller, and persistent volume, where the namespace provisions microservice isolation and scaling. Our ingress controller will set up our communication with the outside world and set that up with our ingress controllers in our services. And then we will have our persistent volume config, which sets up persistent data storage so that we maintain our data even after our Docker containers shut down. And so this is essentially what your project is going to look like if you microservice it. Finally, the last thing we're going to talk about today before we jump into developer and engineer worth, and that's talking about monetary value of a developer or engineer. We're going to talk about, before we get into that, is our Helm package manager. And what Helm is it's a manager for our packages for Kubernetes, simplifying our deployment and management of Kubernetes applications. So what Helm does is it simplifies the way we deploy our applications in a microservice configuration, and it simplifies a lot of the processes in Kubernetes. And it uses Helm charts, which are pre-configured templates that define resources and configurations, enabling developers to deploy complex applications with ease. If you're setting up a really complicated Kubernetes system, I recommend using Helm charts because it really does simplify the process through charts. And what these charts are is that they are defined Kubernetes resources. For example, they do define the Kubernetes resources like our deployments, services, etc., and parameters in a already predefined format. So it's less free-for-all, there's more of a format to it, and it's easier to read than your Kubernetes files. Charts are bundled and stored in repositories or shared locally, so you can package your charts. And then the Helm charts are deployed using the Helm install command, and that will deploy your chart to a Kubernetes cluster. The charts can be customized. Configuring values can be overridden during deployment with values.yaml or CLI arguments. So this means that you can either create a values.yaml file and override our deployment variables, or you can give command line arguments to override our configuration values. So it gives us a little bit more of a customization ability when we're running our application, which is very, very helpful. And so we're going to move on to attendance in a sec, but before we get to that, what I would like to do is I'd like to talk about the big question, which is how much am I worth, or how much should I get paid? So I'm going to go ahead and share a different window here. Let me see. Make selection. We're going to share this window right here. All right. So, as you can see, we have our boring Excel spreadsheet. But this Excel spreadsheet I compiled today. It's based off of an old one that I had built in 2023. And the reason I made this spreadsheet was I asked myself, it's a new year, it's 2025. How much am I worth as an engineer? And this changes from year to year, so I really wanted to update myself on current standards of how much do we get paid. And so the source of this information comes from several sources, including PayScale, I believe, and ZipRecruiter. And I compiled different the percentiles given on these sites in the US for different positions in terms of software engineering, right? So when we're looking at basic software engineering, we have several different levels. When you start as a software engineer, you of course want to get an internship. And that applies whether you are a bootcamp graduate or you are a college, you're in college or you're in university for software engineering. You want to start by getting an internship because that gets your foot in the door with a company, shows that you have project experience and that you've worked on teams before. Following your internship, you want to move into an entry-level or junior position, which is basically your full-time position. Entry-level jobs typically start with the word junior. So you're going to see junior software engineer or entry-level software engineer, right? And so you're looking for a junior level position next. Following that, you move into mid-level, which will either be your basic software engineer. It's also known as SWE1, I believe, or SWE, I believe it's SWE1. Or you could call it a mid-level software engineer. Then following your mid-level career is your senior career. And what your senior career is it's when you essentially have been a mid-level engineer for some time and you're moving up to a team or a project level authority. And actually, we're going to switch over to this chart here because what this table here shows is when you're an intern, you don't need any years of experience. To be an entry-level engineer, you need at least probably 1 year of experience as an intern, and you also need some background educationally. So you either need to have a boot camp under your belt, typically, or you need to have a degree. And entry-level jobs can be pretty easy to get, but they expect you to be in that entry-level position for at least 3 or 4 years, 2 or 3 years, before you move on to a mid-level position. The idea is that when you're an entry-level engineer, you are a trainee, while when you're a mid-level engineer, you are competent. You're competent on different programming languages, you're competent on different programming tools, you also understand some cloud deployment and some DevOps. Now, the difference between a senior engineer and a mid-level engineer is that when you're a senior engineer, you are proficient, meaning that you can handle a project more or less on your own. And you can follow through with deployment and you understand how the deployment pipeline works. You understand how to architect an application rather than just write code. And so there's a lot of differences in scope. And so what we've been talking about, interns will support teams and tasks, while entry-level engineers will work on specific tasks. Instead of looking at the whole project, they'll be assigned tasks within the project and learn how it works within the project. Mid-level engineers should have a project-level knowledge, while senior engineers take more authority over a team. After like 5 to 10 years of being a senior engineer, more like 5 to 7, you'll end up graduating to a staff position, which is the, mega engineering position. And that's with around 12 to 15 years of experience. 12 is pretty much the minimum there. And this means that you are an expert in software engineering. So you understand all the different facets of software engineering. You know how to lead teams, and your goal now is to manage multiple teams. And then following that, you graduate to principal engineering, where you are now in distinguished proficiency. So maybe you have a specialty, but your idea is that you will be working and managing the whole organization. So you'll be managing staff engineers, which manage senior engineers, which manage mid and entry level engineers, as well as interns. So while interns, entry-level, and mid-level engineers all report to a team lead, which is typically a senior engineer, senior engineers report to managers, staff engineers report to senior managers, and principal engineers report to directors. So this begs the question, how much are you worth? And so I compiled statistics over the hourly and salary rates for engineers and developers in different positions. Now, there's a difference between developers and engineers. Engineers typically have degrees starting out. So the idea behind an engineer is that engineers understand the different kinds of software architectures, have worked in different kinds of software architectures, or are learning how to work in them, and can think from a top level all the ways down to the bottom level of coding and design. So all the ways from how does this run on a computer down to how do I write this individual line of code. On the other hand, developers typically graduate from boot camps or are self-taught, have certificates, and have a strong background. However, they didn't go through 4 years of schooling, so they don't have all of the education on data structures, algorithms, probability, calculus, all of that nitty-gritty stuff that you learn in college, which is why college can be a very valuable path. But when it comes down to it, engineers and developers even out in salary around the senior level, and when you become a senior level developer, you're basically an engineer because you already understand and you're proficient in how systems are architected. So you have two paths ultimately, and the idea here is that you can see, hey Alex, do you have a question? I think his mic came unmuted. Let me see. Excellent question. So that really has to do with a couple different factors. What did you get your degree in? Was it STEM focused? Did you learn probability statistics? Did you learn about computer engineering, etc.? I was a computer engineer starting out, so I mainly focused on embedded systems hardware, so hardware for small devices. But I also had a heavy software component where I learned assembly and C++ and a bunch of different languages, and that really led me into the engineering route. Engineering as a degree is just in general, any kind of engineering will also help you move into that engineering route. However, if your degree was more into like fine arts, graphics designs, you're going to have to work harder to advocate for yourself as an engineer, prove that you have architecture know-how, and that you understand how code is run on computers in order to claim an engineering status. It doesn't mean, being a developer doesn't mean that you can't apply for engineering jobs. It just means that when your resume is looked at, they're going to see, hey, they have bootcamp experience, but they're also maybe a UI UX designer, right, or engineer. Well, if they have bootcamp experience, but they also understand interfaces, they might fit really well into the front-end engineering niche, right? Because you're already working with interfaces, you have the technical knowledge to apply, and that's when you come into this weird niche that I call full stack designers, which are designers who know how to design an application, but also how to code it afterwards. And that's more of an engineering form than developing, in my opinion. But again, it is a very subjective idea behind developers and engineers. The main thing is when companies are looking for engineers, they're looking for people who know how to not only write code, but also know how to architect it. Does that help? Sweet. And so here you could tell there is a bit of a discrepancy between engineers and developers. Developers get paid a little bit less. However, the difference is not too big. And up here, I've calculated that, actually it's on this dashboard page here. The difference between a developer and engineer in entry-level positions is about 15%, 15 to 16. And same thing for mid-level or normal software engineers. However, when you get to the senior level, they only differ in about 5% in salary and pay. And then in staff and principal engineer, it doesn't matter. So that is one thing to look at, is when you're in entry level or mid-level position, you're going to get paid a little bit less as a developer, but it starts evening out when you have 7 years of experience. So again, now we're asking the question, how much should I get paid? Salary-wise, entry-level engineers get paid on average $77K, and entry-level developers get paid $65K, which is already decent as it is. That'll get you far in Austin. When you get to mid-level and have about 4 to 5 years of experience, you'll get paid around $100K. And with developers being a little bit less, but it's around $100K. Senior engineers and developers get paid around $120, $130, and then staff engineers get paid at $160. Now, one thing you might notice is that principal engineers, your value seems to go down, and this kind of trend was found pretty much everywhere where I went, and I think it's just because you cap out your salary around staff engineering, and then principal engineering is more like it's more of a title than actual pay, right? It's not a pay raise, but it's a title that says you're not only knowledgeable in your field, but you are distinguished, you are a icon, or you've done big things in your field. So principal engineers, it's not necessarily that they get paid less, but they kind of cap out their salary at staff engineering. So the goal is ultimately to make it to staff within 12 to 15 years of becoming a developer or engineer. When you're charging an hourly rate, internships for engineering is on average around $26 per hour, but when you get into entry-level positions, it doesn't go up by much. It may be around $30 an hour. Mid-levels, you want to charge around $50 an hour. And if you're senior level, you can charge up to, I'd say usually 75 is my maximum as a senior engineer. But sometimes I push my contracts into a little bit more than that, depending on the requirements of the contract. If I'm managing a project all by myself, it's something that is taking up a lot of my time, etc. And I'm deploying it, managing it, making sure it's set up right, and it's efficient, and managing all the bugs. I'm out on call. Then I push this number up higher because I work as a senior engineering contractor. And then staff engineers typically don't get paid hourly. Typically they're employed by big companies. The only way you get a staff title or a principal title is when you work for a big company and a big company hires you as one. And so to level up to this level, you don't usually get paid hourly, but you'd get paid around $85 an hour. And so here we have our low, medians, and high values for payment. And then we also have our average and then our developer average here. And you can see that low for an intern is around $18 an hour. High is around $35 an hour. And median is around $25 an hour. And then you could see that in terms of salary, a low salary for a entry-level engineer is about $62K, and a high salary is about $100K. And this kind of just follows suit upwards. So I feel like this was something important to note, due to the fact that if you are a engineer or developer in this class and you want to know your worth, these are your numbers right here, salary and hourly. And if you want to hire somebody as an entrepreneur and you're looking to hire developers, this is how much a developer would typically cost in the United States. Now, I have another spreadsheet that has developer salaries and hourly rates for international because I've traveled to over 2 dozen countries and have logged and met a lot of different people and also know the sites to go to find that information. But when we're looking at US software engineering, this is what you would typically pay. And this is what it typically means. Last thing to note is that this is the salary rates. These are the salary rates for other professions within the tech field. So we have our software engineer with a mid-level capping out at around 110, 111K. However, graphic designers make 50% less. They make around 50K a year as salary. UI UX is typically 90K as, a mid-level 5 to 10 years of experience. You might notice that if you're specializing in front-end, back-end, DevOps, or cloud, or you can make higher than a software engineering salary just by specifically applying to specialized positions instead of being a generalist. And this really comes down to the fact that generalists are less highly valued than specialists. Specialists get paid more because they have a specialty in an area that a company is looking for. Where you're going to get hired as a generalist is in startups, which typically pay less. So if you want to be a generalist and work on general projects, that's okay. You can label yourself as a software engineer and make a solid salary. But if you want to make more than that solid typical salary, I would recommend naming yourself either a front-end engineer or a back-end engineer or another engineering form and marketing yourself as that, applying to positions as that, and your LinkedIn should say front-end engineer. Your resume should say it. Everything should be corresponding. And then finally down here we have our embedded systems, our AI engineering, and our QA engineering. QA engineers do get paid less due to the fact that their job doesn't always have to do with high-level code. A lot of it has to be running tests and seeing the outputs. Another thing to note is that cloud engineers and AI or machine learning engineers get paid most out of all the engineering fields. So I hope this helps. This is essentially a resource that I have created for myself to be able to access, and in this presentation I have passed it on to y'all so that you know how much you're worth as an engineer. And of course this comes from a bunch of compiled data, and it's not perfect, but it gives me at least some insight on how much I should be pricing myself in 2025. And I hope it gives you some information on where your career is heading in terms of projects, what you're learning, and how you're growing as an engineer yourself or a developer. So we're going to go ahead and stop sharing this screen, and we're going to move back to our attendance form, and then I'm going to give you all some time to fill out the attendance. And after we fill out attendance, we are going to have our project check-ins. So everybody, whether you're part of the program or not, please fill out your attendance. It gives us great feedback on what we can improve on, what you like seeing, and how we can make this program even better, because as 2025 progresses, Hispanic Hackers is putting on another Code Foundry. We believe that we're going to push it back to either May or June, but it's going to happen and it's going to be bigger than this one. So we're really excited about that. So please give us feedback. Please fill out the attendance form by scanning this QR code. And then if you're not part of the program officially and you don't have any questions, feel free to jump off. If not, if you do have questions, please stick around. And thank you for joining us. We are happy to be here. And if you have any questions, want any resources, looking for some connections, please let me know. Does anybody have any questions? Yeah, I can hear you. So recordings of Code Foundry are posted on the Code Foundry document. So we have a take-home document where we post take-home videos for our program followers to watch, as well as recordings of our lectures. And so I just put it in the chat just now. Feel free to take a look at that, and it has a list of our homework, etc., etc. So yeah, hope that helps. Mhm. We went through AI as a brief overview in one of these presentations, I think before winter break, and we did talk about it then. However, it was very high level. We've had meetings before where we had AI experts. What I recommend there is, if you want to dive into AI, go ahead and always check out our meetup page for socials or other meetings where it might be AI focused. And in addition to that, check out Tequeria, which is another Hispanic organization that that has more socials than us, and does more formal meetings than these programs. I hope that helps. It's called Tequeria. It's TECHQUERIA. Let me find it. No problem. Here it is. No problem. Hope that helps. Awesome. If anybody has any other questions, let me know. Fill out that attendance form, and then in 2 minutes, we'll start going through project updates. Okay, we're gonna go ahead and start our project check-ins. The last thing to note is that we'll have 2 take-home videos coming out on tomorrow and Thursday, along with this video recording. And then the one homework assignment that you do have is to continue React Native development of your mobile application. In addition to that, I would like for everybody to start thinking about presentations for our final meeting, which will be at Capital Factory in 2 weeks. So we have 2 weeks to kind of wrap things up in a way that at least you have a bow tie on it and slap it on and say, this is our stopping point for this program right now. And I'm really excited to see, what y'all's outcomes have been. I know that we have 2 or 3 ongoing projects that have been pretty dedicated, so I'm really appreciative of y'all. And so with that, Josh, do you want to go ahead and start? Yeah, I got you. How's your project going? Yeah. Hmm. Nice. I'm really excited about it. In terms of open AI, how much have you been keeping a track on like costs and how much it's costing you? Okay. Like, okay. That's not bad. Yeah. Sweet. Okay, I was just wondering because I've worked with ChatGPT before, and I know that you do have to like fine tune the restrictions or the limitations on there just to make sure you don't get charged a bunch. But it sounds like y'all are doing good. Okay. Yeah. Yeah, that makes sense. Okay, sweet. I'm glad to hear that things are going well. Just keep in mind that when we do our final presentations, I'd love to see like a PowerPoint with all the like the maybe some different components or whatever. Like I got to think about what should go in that, but I'll send that out soon. Um, I guess more like a marketing presentation kind of deal. I'm I feel like I've been learning a lot through this process, and I know next time that I want to get investors for the next program to like watch the final presentations and kind of blow it out. So I'm really excited about it. But thank you all for so far participating and showing up and doing all of that the good things that are keeping this program running. Thank you, thank you. Do you have any questions for me? Awesome. Well, wishing y'all lots of luck and lots of hard work and all of that for the next week. And I'll see y'all on next Monday on online. Um, Sweet. Alex, how are you doing on your project? Hmm. Mm-hmm. Okay. Mm-hmm. Yeah. Mm. That's an awesome reroute, honestly. Um, because that's something that could help a lot of people too, you know? Hmm. Yeah. Yeah, no, I got you. Do you have any questions for me? Gotcha. Yeah, message me. Let's figure out a time either tomorrow or Thursday. Those are like my open days typically, and would be happy to. Sweet. Yeah, of course. Have a good night, and I'm looking forward to seeing you at next meeting and talking with you this week. Cool. Have a good one. Jeff, how are you doing? Yeah, yeah, I gotcha. Um, I gotcha. No, don't worry. Don't worry about the project. I did see that you did submit a question. It said more security. What do you mean by that? Hmm. Hmm. Yeah. Um, no, I know what you mean. Yeah, I gotcha. So there are known vulnerabilities in code because libraries will just, like, when a library gets breached by a hacker, you know, we, yeah, exactly. And so that happens all the time. And so, of course, there's logs on uh, known breaches in code, libraries, etc. You can run tools and specific libraries for checking other libraries. I think it's more of using command line tools to do so. I forget what the name is, but I used to work for a cybersecurity company, so we were doing that. What kind of application is it? Is it like a Node.js application, or is it what is it using? Okay, gotcha. Yeah, so in terms of, go ahead. In terms of Java, you're going to want to make sure that you use appropriate namespaces and all of that on like a very surface level when it comes to cybersecurity, just so that you don't expose logic that doesn't need to be exposed. And then in terms of Python, you're going to want to run scans on the libraries that you use. Um, and then depending on how you package it, you're going to want to assess for vulnerabilities there too. You could also implement DevOps tools. So you can implement tools on the production pipeline, which will test to see if there's any way for hackers to get in using known vulnerabilities as well. Yeah. I get surprised when I see people using Java at all, honestly. It's a bit of an outdated application, but it is great for legacy code and for when you want to have enhanced security measures. It's a bit of a useful language there, but it's yeah, yeah, that makes sense. I mean, it is still a popular language, but it isn't as efficient or lightweight as other programming languages. Like, I mean, these days a lot of people advocate for Golang or, I mean, Python is more of a data scripting language, but Golang, I feel like C++ is pretty effective, but it is also a little bit older. Rust, a lot of people talk about Rust and rave about it, but yeah, that is very true. It is very different. But okay. Well, do you have any questions for me? Any other questions? Yeah, I think it's gonna either be May or June. I want to. My goal is to get it a little bit better set up. I feel like for example, this meeting, 30 people signed up online, but only about 10 showed up. And I feel like a lot of that has to do with the fact that it's on Discord and not a lot of people want to get on Discord. So that's a bit of a barrier. I also want to make it a little bit um, more more better teaching, right? Like I want to make there be interactive portions where you meet with your team, you talk with your team during the meeting, and work on parts of your application, right? Things like that. But yeah, I'm really excited about it. makes sense. Discord's really great, but it's good for when you have an online group rather than a group that meets in person or is like, you know, locally connected. Uh, because we get a lot of traffic through from Capital Factory, but then when people see our group on Capital Factory and then they find out that we only meet on Discord, they get turned off, I think. So that's something I'm learning. I'm learning a lot through this process. This program. Yeah, I have. We do like those hybrid meetings at Capital Factory, but then for the rest of the weeks you have to find a way to host it, like some place to host it, because Capital Factory only hosts this 1 week a month. Um, so it does complicate. Yeah. Uh-huh. Damn, that's crazy. That's a lot.